Swayam Prabha. Digital India. Educated India.
In the last class we have seen element equations development for two dimensional general boundary value problem using 4 node element. We started with governing differential equation, applied Galerkin criteria, and then applied Green's theorem, and then later we substituted approximation of trial solution and derivative of trial solution in terms of finite element shape functions, and we obtained complete element equations for two dimensional general boundary value problem for 4 node quadrilateral element. I will just briefly summarize what we have done in the last class. So, the complete element equations can be written in standard form by defining following matrices, in which each of these quantities kx, ky, kp, k alpha, rq, r beta are defined here, and this equation can also be compactly written as kd equal to r, where contribution to k comes from kx, ky, kp, k alpha, and contribution to r comes from rq and r beta. And if you see these each of these components kx, ky, kp, k alpha, r beta and rq, some of these are area integrals and some of these are boundary integrals. So, let us discuss in today's class how to evaluate each of these integrals. First let us look at area integrals, evaluation of area integrals, and later let us look at evaluation of boundary integrals for given a 4 node quadrilateral element. And these integrals can be quite complicated and usually require numerical integration, because once we start using a bilinear element or quadratic element, these integrals are no longer going to be constant, unlike in 3 node triangular element which is linear. So, we need to adopt numerical integration. So, all those details will be illustrated in the numerical examples that we are going to see in today's class. So, let us start with discussing how to evaluate area integrals. Area integrals kx, ky, kp, rq can be evaluated by using following relationship from calculus relating differential area in xy domain to its equivalent in the mapped domain SNT. So, we are working for the actual element, we are working in xy domain, and that element, actual element, we are going to map it onto a parent element which is in SNT domain. So, we need to know what is the relationship between the differential area in xy domain to differential its equivalent or differential area in mapped domain SNT. So, this is how it is related. Differential area in xy domain is related to its equivalent in mapped domain SNT via this relation, that is dx times dy is equal to determinant of j times ds dt, where determinant of j is determinant of Jacobian matrix that we get from partial derivatives of x with respect to s, x with respect to t, y with respect to s, y with respect to t. So, once we have this relation of differential area from xy domain to SNT, its equivalent in SNT domain, we can write let me go back. We can write, we can evaluate the matrix Kx. For example, consider evaluation of matrix K using Gaussian quadrature. So, this is how Kx matrix is defined, integral over area Kx times Bx transpose. So, we need to evaluate Bx transpose times Kx over this area. These limits of integration can be changed to -1 to 1 in the parent domain using the relation that dA is equal to Jacobian determinant of Jacobian times ds dt. We can change the limits of integration as given in the equation, which can be further approximated by taking certain number of integration points along s direction and t direction, and here the formula is written for the case where m number of points are taken along s direction and n number of points are taken along t direction. So, if you see this formula, SNT, SI, TJ are locations of Gauss point, WI, WJ are corresponding weights. For example, for 2 by 2 integration, Gauss points are located at plus or minus 0.57735 and weights at all plus or minus 0.57735. That means we need to use all kind of combinations to get all the coordinate of all the 4 integration points, and weights at each of these integration points is going to be 1, because weight in the s direction times weight in the t direction is 1, because weight in the s direction is 1 and weight in the t direction is 1. So, we need to evaluate, if we decide to use 2 by 2 integration, we need to evaluate, or the integrand needs to be evaluated at 4 points and the resulting matrices needs to be summed up, and whatever this formula that is shown in that Kx is not assumed to be function of spatial coordinates x, y or SNT if coefficient is not constant, unlike what is shown here. First we need to express this Kx in terms of SNT before we go ahead with numerical integration. How to express Kx as a function of SNT? For that we need to use isoparametric mapping, which relates xy to SNT. So, let us take a problem and try to understand various steps in the evaluation of the area integrals. So, this is what I mentioned. If coefficient Kx is not constant, it must be first expressed in terms of SNT using isoparametric mapping before proceeding with numerical integration. So, now let us take an example, evaluate matrix Kx for the 4 node quadrilateral element shown below. Assume coefficient Kx is equal to 1, use 2 by 2 integration. Here coefficient Kx is taken as a constant, which is equal to 1, and the 4 node quadrilateral element is shown in the figure. Nodal coordinates of all nodes are indicated in the figure. So, we can easily find what are the nodal coordinates, and we can put all the x coordinates of all nodes in one vector, y coordinates of all nodes in another vector. So, nodal coordinates can be written in this manner. And we need to evaluate this integral using 2 by 2 integration, that means 2 points in the s direction and 2 points in the t direction. So, we need to know what are the points, and if you recall earlier I gave this information for 2 by 2 integration, 4 points, the locations of 4 points are as shown in the figure, the corresponding coordinates can be obtained by all kinds of combinations of Si and Tj, which are equal to plus or minus 0.57735, and weights at each of these integration points is obtained by weight in the S direction times weight in the T direction, which is going to be equal to 1 at all the 4 points. So, with this we get the we can easily figure out what are the locations of all the 4 integration points. So, now our job is to evaluate integrand using these weights and coordinates at each of the 4 integration points. So, now let us start taking one of the point. Let us say the point, the first point that we chose is S is equal to 0.57735, T is equal to minus 0.57735. So, at this location we need to evaluate Bx vector. To get that, we need to calculate what is partial derivative or derivative of shape function with respect to S, which is given here by substituting all the values of S and T, and simplifying we get this. Similarly, we can get derivative of shape function vector with respect to T, and simplification of that gives us this. Once we have these 2 vectors, we can easily calculate what is partial derivative of x with respect to S, which is given by this formula, and by substituting both the vectors and calculating the value, it turns out to be that is minus 0.05. Similarly, other quantities, partial derivative of x with respect to T, partial derivative of y with respect to S, partial derivative of y with respect to T can be calculated. Once we have all these quantities, we can easily calculate what is determinant of Jacobian, and once we have determinant of Jacobian, we can easily calculate what is B matrix Bx vector. So, once we have this Bx vector, we are ready to evaluate integrand value at the integration point that we have chosen, that is S is equal to 0.57735, T is equal to minus 0.57735. So, substituting Bx vector, Kx is constant, which is equal to 1, and determinant of J, we can evaluate what is contribution of the contribution that comes from first integration point to the matrix Kx. So, carrying out vector multiplication, we get this matrix. So, this is contribution to Kx matrix from first integration point that we have chosen. So, similar procedure we need to follow for the other 3 integration points. Details are given here. Let us go through those quickly. So, this is a second integration point that is chosen, and shape function vector derivative with respect to S, shape function vector derivative with respect to T, and once we have that information, we can easily calculate what is derivative of x with respect to S, derivative of x with respect to T, derivative of y with respect to S, derivative of y with respect to T, determinant of Jacobian, Bx vector, and then once we get Bx vector, we can easily calculate what is Kx times Bx transpose times determinant of Jacobian. Once we do all that, we get contribution to Kx matrix from second integration point that we have chosen as this one. So, similar thing we need to repeat for point 3 and point 4. Details are given here. Point 3 is chosen as s is equal to minus 0.57735, t is equal to 0.57735. Derivative of shape function vector with respect to s, derivative of shape function with vector with respect to t, derivative of x with respect to s, x with respect to t, y with respect to s, y with respect to t, determinant of j, bx vector, and once we can calculate bx vector from that information, and once we get bx vector we can calculate what is contribution from this third integration point to the matrix Kx. Similar operation can be repeated for the fourth integration point. Derivative of shape function vector with respect to s with respect to t, derivative of s with respect to x with respect to s, x with respect to t, y with respect to s, y with respect to t, determinant of j, and then bx vector. Once we get bx vector we can do kx times bx transpose, and once we do that kx times bx transpose times determinant of j. Once we do that we get contribution from fourth integration point to the stiffness matrix as this, and now we need to sum up all the contribution from 4 integration points and we get Kx matrix as this. So, this is how we can use Gaussian quadrature to evaluate this Kx matrix. So, this is how we can evaluate area integrals. So, now let us discuss how to evaluate boundary integrals. Before doing that, please recall these are the two boundary integrals which we need to evaluate, k alpha and r beta, and the terms k alpha and r beta require integration along boundary of the element. And since we are dealing with 4 node quadrilateral element, since the boundary consists of 4 line segments, 4 separate cases must be considered depending upon the side along which natural boundary condition is specified. Please note that we need to evaluate these boundary integrals only along the side on which natural boundary condition is specified. For each side the coordinates s for actual element and corresponding coordinates s for the parent element are shown, and the coordinates for the actual element along each side is denoted with capital S, and for parent element it is denoted by small s, and it is shown in the figure here. So, this is actual element, the figure on the left hand side is actual element, the figure on the right hand side is parent element. You can see capital S goes along each edge, capital S goes from 0 to length of that edge or length of that side, whereas small s along each of the sides goes from -1 to 1. And shape functions for each side can be written by substituting shape functions for each side of the parent element can be written by substituting constant coordinate into the shape function expressions. You already know what are the shape functions of 4 node quadrilateral element, 4 node quadrilateral element in the parent domain, parent element domain S and T. We already know the shape function expressions. In that, shape functions for each side can be written by substituting constant coordinate value into the shape function expression. Since there is only one variable, For each side all shape functions are expressed in terms of small s with positive directions of small s for each side as shown in figure. And you can also notice that the trial solution is going to be linear along each side and depends on only the two end values. So, this is what I mentioned, along each side either s or t is constant. Shape functions for each side can be written by substituting whichever is constant out of this s or s and t, whichever is constant, by substituting that constant coordinate value into the shape function expressions. Since there is only one variable for each side, either s or t, all shape function expressions are expressed in terms of s with positive directions of s for each side shown in figure. So, now let us write the shape function vector along each of these sides. For side 1 2, you can easily see from the parent element along side 1 2 t is going to be minus 1. So, you know the shape function expressions of all the 4 nodes for 4 node quadrilateral element in the parent domain. So, in those expressions you substitute t is equal to minus 1 and put all the shape functions in a vector form. This is how shape function vector is going to look for side 1 2, whereas goes from minus 1 to 1. So, similarly for other sides, side 2 3, 3 4 and 4 1, we can write shape function vector by substituting the corresponding values of s and t. So, we need to evaluate this. Consider evaluation of r beta with beta given along side 1 2. So, beta value assume that is given. So, we need to evaluate r beta along each of these boundaries. R beta is integral beta n ds, capital ds, sorry, d capital S. So, here we will illustrate the procedure by taking side 1 2. So, that is why it is written side 1 2 there. So, to proceed further we require what is the relationship between a differential element in the actual differential, small differential element taken along each of these sides in the actual element domain and small differential element taken along each side in the parent element domain. So, we require to find what is the relationship between d capital S and d small s. For that we require to find isoparametric mapping along each of these edges or sides. So, isoparametric mapping for side 1 2 is x is equal to n1 x1 plus n2 x2, because n3 and n4 are going to be 0 along side 1 2, and this gives us relation of x in terms of s, and from there we can find what is derivative of x with respect to s. Similarly, y is equal to n1 y1 plus n2 y2, because n3 and n4 are 0 along side 1 2, and once we simplify and take derivative, that is derivative of y with respect to small s, we get this, and taking, and finally we are doing all this. Please note that we are doing all this because we require to find what is relationship between a differential element in the actual domain, relationship between differential element taken along a side in the actual element domain, and what is its relation with a differential element taken in the along each of the sides in the parent element. So, Jacobian, the Jacobian of transformation from capital S to small s is defined as, so this is what we are looking for, d capital S divided by d small s. So, that is what Jacobian j side 1 2, and to get that let us closely look at this figure which shows only side 1 2 in the actual element and also side 1 2 of the parent element, and the actual element is shown in figure on the left hand side and the parent element side 1 2 is shown on the right hand side, and ds d capital S small differential element along side 1 2 in the actual element is indicated there. Actually it should be d capital S, in the figure it is printed as d small s, please make that correction. D capital S can be resolved as dx and dy along x and y, and it can be easily noted that the relation is d capital S is equal to square root of dx square plus dy square from Pythagoras theorem. And now we just found what is d derivative of x with respect to s, derivative of y with respect to s. So, now we have this relation, that is d capital S is equal to square root of dx square plus dy square from the geometry of the actual element. So, if we divide both sides of this equation with d small s, we get this relation where we can substitute whatever we obtained from isoparametric mapping, that is derivative of x with respect to s, derivative of y with respect to s. Here there is a mistake, it should be dx over ds square plus dy over ds square. So, y instead of y x is printed. So, this is the relation. So, L over 2 L over 2 L12 over 2, that is what is j for side 1 2. This L12 length of side 1 2 can easily be obtained from the coordinates of the nodes, and so the relation is this one, d capital S over d small s is equal to L12 over 2, and which can be rearranged in this manner. So, we can replace in the integral wherever we see d capital S, that we can replace with L over 2 d small s, where small s goes from -1 to 1. So, the limits of integration also gets changed. The boundary integral can now be evaluated as follows using one dimensional Gaussian quadrature, and to get the points and weights we need to refer the tables that we already have from the earlier lectures. So, the previous integral now takes this form, integral on side 1 2 is replaced with integral from -1 to 1, because d capital S is replaced with j times d small s, and now substituting the shape function vector along side 1 2 we can evaluate this integral once beta is known. In this manner using one dimensional Gaussian quadrature. Similarly, since k alpha is also a line integral or boundary integral, we can evaluate k alpha also in a similar manner. The integral k alpha can be evaluated using the same shape function and Gaussian quadrature, and the procedure is same if natural boundary condition is specified along any other edges or sides. The only difference is that different shape functions are 0 along different sides. I think you agree with me on that, that is different shape functions are going to be 0 along different edges. So, we need to take care of that when we are evaluating these integrals, and we need to be careful along which side we want to evaluate. We need to substitute corresponding shape function vector, and all these concepts will be made clear once we solve a numerical example. So, the procedure is same if natural boundary condition is specified along any other edges or sides, with only difference is shape functions are 0 along different shape functions are 0 along different sides. So, now let us take an example, evaluate r beta for a 4 node quadrilateral element, and beta is given as -1, and the coordinates of all nodes for this 4 node quadrilateral element are given here, and use 2-point integration. So, these vectors of nodal coordinates are required for us, because we require to find what is isoparametric mapping, to find the relationship between d capital S and d small s. So, for that we require all this information. So, now r beta is evaluated using this formula, for which we require shape function vector along side 1 2, as we already discussed. Shape function vector along side 1 2 is given by this, and length of side 1 2 is also required, because Jacobian is length of side 1 2 divided by 2. So, we can get that, or we can calculate L12 from the information of the nodal coordinates using the formula like this. And now we need to use 2-point integration. So, this is the first point, and weight at this point is equal to 1. So, evaluate all the quantities, that is integrand at this integration point by substituting S is equal to 0.57735. Simplification of that gives us this. So, this is the contribution from the first integration point to the vector r beta. Similar operation we need to repeat at the second integration point, and we get the contribution from the second integration point to the vector or to the integral r beta, and finally when we sum we get r beta vector. So, this is how we can evaluate boundary integrals, whether it is k alpha or r beta. Now, let us look at 8 node, let us look at similar kind of equations for 8 node serendipity element, that is 8 node serendipity element for 2-dimensional boundary value problem. Before that, why this 8 node serendipity element is required? To form it is a higher order element, and also curved boundaries can be modeled using this element. So, 8 node element, actual element is shown, and the parent element in SNT domain is also shown here. So, consider an 8 node element shown here, and also parent element is also shown on the right hand side as figure B, and let the coordinates of actual nodal coordinates of actual element be x1 y1 of node 1, x2 y2 of node 2, like that, and we can put all these nodal coordinates in 2 vectors, all the x coordinates in one vector and all the y coordinates in another vector. So, we can define 2 vectors xn and yn in this manner, because we, if it is advantageous to put the x nodal coordinates and y nodal coordinates in this manner, because we can easily evaluate by vector operations, what is partial derivative of x with respect to s, x with respect to t, y with respect to s, y with respect to t, to calculate determinant of Jacobian. And we also require shape functions of 8 node serendipity element in the parent domain. We already discussed how to get the serendipity element shape functions earlier. So, the same shape function expressions are reproduced here. Shape functions for parent element are as follows: n1 to n4 are shown here. Similarly, n5 to n8 are given here. These shape function expressions are required for isoparametric mapping, and all these shape functions we can put them in a vector n. Since we have shape function, all the shape functions expressions, we can easily calculate what is derivative of shape function vector with respect to s, derivative of shape function with respect to t, shape function vector with respect to t, because these two vectors are required for finding determinant of Jacobian. So, now let us see what is isoparametric mapping for 8 node serendipity element. So, this is how isoparametric mapping can be performed, and which is similar to 4 node quadrilateral element, except that the shape function vector is now involves 8 shape functions n1 to n8, xn involves x coordinates of all 8 nodes, similarly yn involves y coordinates of all 8 nodes. So, once we have this, we can easily calculate what is j and determinant of j, and from there we can calculate. For that, for getting j and determinant of j, we require derivative of x with respect to s with respect to t, y with respect to s, y with respect to t, that can be calculated using these expressions which are given here. And also we require x y derivatives of entire shape function vector. Whatever we calculated, those are shape function vector derivatives with respect to s and t, but we also require with respect to x and y. So, we can obtain that using chain rule or through this relation bx, that is shape function vector derivative with respect to x, similarly shape function vector derivative with respect to y. Using the parent element shape functions, the trial solution and its derivative can symbolically be written as follows: t is the field variable, t value at any point is given by n transpose d, d consists of all the nodal unknowns t1 to t8, and then we can also calculate derivative of t with respect to x with respect to y through this formulas. So, once we have all this information, substituting the trial solution in the Galerkin criteria, which we already have when we are looking at 4 node quadrilateral element, we looked at in detail Galerkin criteria, Green's theorem and all that stuff. So, substituting trial solution and its derivative into the Galerkin criteria and writing all 8 equations together in a matrix form, we get. Earlier when we are dealing with 4 node quadrilateral element, we got 4 equations. Now, since we are dealing with 8 node serendipity element, we get 8 equations. So, writing all 8 equations together in a matrix form, we get this. So, complete element equations can be written in a standard form by defining the following matrices. This equation looks similar to what we obtained for 4 node quadrilateral element, except that the dimension is more here. It is going to be, all these matrices are going to be 8 by 8 and vectors are going to be 8 by 1, whereas earlier we have 4 by 4 and vectors of dimension 4 by 1, and the details of each of these is similar to that of 4 node quadrilateral element. So, this is how element equations looks for a general 2 dimensional boundary value problem with 8 node, adopting 8 node serendipity element. So, now let us look at or discuss how to evaluate each of these area integrals and boundary integrals, and also illustrate by looking at some examples. So, the area integrals, evaluation of area integrals. The area integrals can be evaluated using Gaussian quadrature, as we did for 4 node quadrilateral element, and so Kx matrix can be evaluated using this. This is exactly same as what we did for 4 node quadrilateral element, and Si, Tj are the locations, Wi, Wj are the corresponding weights, and rest of the details are similar to that of 4 node quadrilateral element. So, now let us take an example. Evaluate matrix Ky for an 8 noded element if the nodal coordinates are as given here, and assume coefficient Ky is equal to constant, is a constant equal to 1, and show calculations for one Gauss point and adopt 3 by 3 Gaussian quadrature. So, we need to know what are the weights and coordinates when we use 3 by 3 Gaussian quadrature. Already we discussed this earlier, and these are the coordinates and weights in the s direction and t direction. Using Cartesian product of these coordinates, we get coordinates of all the 9 integration points. Please note that here we are going to get total 9 integration points, because we are using 3 by 3 integration, and similar to that of 2 by 2 integration, weight in the s direction times weight in the t direction. If we find, that gives us total weight at a particular point, but here weight is not going to be constant, is equal to 1, as in 2 by 2 integration it is going to be different for different points, depending on the location of point it is going to be different. So, for 3 by 3 integration, 9 points in total, one of the Gauss point is located at this, and calculations details are going to be demonstrated or illustrated for this particular point. Calculations are shown for this point. Complete integral involve performing similar calculations at other 8 points, adding results together. So, let us take this point, and here for this particular point weight in the s direction is going to be 5 by 9 and weight in the t direction is going to be 8 by 9. So, total weight is going to be 5 by 9 times 8 by 9. So, this is a point, and this is what I mentioned about the weight. So, rest of the details are similar to that of 4 node quadrilateral element, except that dimensions of vectors are going to be now 8 by 1 or 1 by 8, depending on how you put that vector. This is derivative of shape function with respect to s, shape function derivative with respect to t, and once we have this information we can easily calculate what is derivative of x with respect to s, derivative of x with respect to t, y with respect to s, y with respect to t. And then determinant of j, then by vector, all this follows mechanically once we get the information about point and weight. So once we get this vector, multiply coefficient ky with by transpose Jacobian, determinant of Jacobian times weight. After doing vector multiplication we get this matrix. So this is at one integration point. Similar operation we need to repeat at remaining 8 integration points and sum them up to get the total value or the value of matrix ky from contribution from all the 9 integration points. So this is how we can evaluate area integrals for 8 node serendipity element. So now let us discuss about boundary integrals. Once again these are the two boundary integrals. If you look back the element equations, these are the two boundary integrals. Boundary terms k alpha r beta must be evaluated separately depending on the side along which natural boundary condition is specified. So this we already discussed when we are looking at 4 node quadrilateral element, and also for each side the coordinates s for actual element and the corresponding small s for parent element, we need to find also the relation and they are shown here, actual element, parent element. And if you see there are 3 nodes along each side, so trial solution now it is going to be quadratic along each side and depends upon 3 nodes on that side. And if you take, let us take this parent element, and for any of the edges, let us say one a side containing 1, 2, 3 nodes, the shape functions of rest of the nodes other than 1, 2, 3, shape functions of those nodes are going to be 0 along this side 1, 2, 3. Similarly along side 3, 4, 5 except 3, 4, 5 other shape functions, other nodal shape functions are going to be 0 along that edge 3, 4, 5, similarly for other edges. So for side 1, 2, 3 we already have shape function expressions for 8 node serendipity element in the parent element domain. So in those expressions substituting t is equal to -1 for side 1, 2, 3, similarly substituting s is equal to 1, t is equal to s for side 3, 4, 5, and for sides 5, 6, 7 setting t is equal to 1, s is equal to -1, and for side 7, 8, 1 setting s is equal to -1, t is equal to -s, we get expressions or shape function vector along each of these sides, along each of the 4 sides. So those are given here where s goes from -1 to 1. So this is the shape function vector along side 1, 2, 3. Similarly for side 3, 4, 5, side 5, 6, 7, for side 7, 8, 1. So, we got shape function vector along each of these sides. So, we can evaluate boundary integral r beta or k alpha, r beta with beta given along side 1, 2, 3 is illustrated here. So, for that evaluation we require shape function vector along side 1, 2, 3, and also we require the information of how the differential element taken along side 1, 2, 3 in the parent element is related to differential element along the same side in the actual element. So, we require to find what is the relationship between d capital S and d small s. For that we require to do isoparametric mapping along this edge. Isoparametric mapping gives us this, and here x is equal to n1 x1 plus n2 x2 plus n3 x3, because shape functions of other nodes along this side 1, 2, 3 are going to be 0. Similar is the case for y. Once we have these relations x in terms of s, y in terms of s, we can take derivative of x with respect to s, y with respect to s, similar to the way we did for 4 node quadrilateral element. Once we get these two quantities, and here side 1, 2, 3 for the actual element and parent element are shown, and similar to that for 4 node quadrilateral element, d capital S is given by square root of dx square plus dy square. When we divide that equation on both sides with the ds, we get the equation, or we get the relation for Jacobian along side 1, 2, 3. So, once we have this, we can change the limits of integration and use one dimensional Gaussian quadrature. This is for integral r beta. Similarly, we can evaluate k alpha using the same shape functions and using this formula. The procedure is same if natural boundary condition is specified along any other edge or side. The only difference is that different shape functions are 0 along different sides. And now let us quickly take an example. Evaluate k alpha for 8 node element if nodal coordinates are the x coordinates and y coordinates of all 8 nodes are given here, and assume alpha is equal to 1 along side 1, 2, 3 and use 3 point Gauss quadrature. So, we require to evaluate this integral. For that we require shape function vector along each of these sides, or sorry side 1, 2, 3 along side 1, 2, 3. The shape function vector along side 1, 2, 3 is given by this, and also derivative of x with respect to s with derivative of y with respect to s is given by this. From there we can find Jacobian, and now taking each of the integration point. This is first integration point, details are given here, the shape function vector and substituting shape function vector and Jacobian along side 1, 2, 3 at this integration point, we can get the contribution of the first integration point to k alpha matrix. Similarly, second integration point contribution by taking shape function vector at this point and the third integration point contribution, and summing all the contributions we get k alpha matrix. So, this is how we can evaluate area integrals and boundary integrals for both 4 node quadrilateral element and 8 node serendipity element.